Hi folks, this lecture is on energy and open systems. So if we're just interested in tracking the energy in a single object and its energy is changing, what other kinds of variables and terminology do we use to discuss the changing energy in a single object? And those variables are known as work and power. One of the tricky things about this little chunk here is that you guys have used the words energy, work, and power lots in your lives, and now I'm giving those words very specific meanings. So please pay attention to the way that we use those words and what they mean compared to the way you use those words in your everyday speech. So work is just another name for change in energy. We define work as an object's gain or loss of energy. It happens when an object's energy changes due to the fact that energy is transforming from one type or another, or because the object's gaining or losing energy to another object. Positive work increases an object's overall energy or increases one type of energy, and negative work decreases it. It should be noted that because of conservation of energy, every time an object experiences a positive work of some type, there's going to be some sort of equal and opposite negative work somewhere else in the universe. Sometimes we're going to try to track all the work in a closed system and the total energy will be conserved, and other times we're just going to focus on the work on a single object whose individual energy types or type will change. So let's say that you have a broken down car and you'd like to move it. If we wanted to calculate how much work it's going to take to get that car going, we're going to have to take into consideration the fact that you're taking some of your body's chemical energy and you're transferring it into the kinetic energy of the moving car. How do we get energy from one object to another? Well, if you listen to Grandmaster Jedi Master Yoda here, he'll tell you that you're using a net force. So just like when we were talking about momentum, transferring momentum from one object to another, forces are the mode by which we transfer energy from one object to another as well. So is net force the only variable that matters for work? Well, if you push a car 5 feet and use the same amount of net force to push a different car 10 feet, different car with the same mass, which one's going to be moving faster? Well, hopefully it's kind of obvious to you guys that if you keep pushing that car for a further distance, it ends up moving faster, which means that whichever car is moving faster is going to gain more energy because that kinetic energy of motion depends on how fast an object is moving. And it should take more work because if an object's changing energy more, work by definition is change in energy. So it's not just the amount of force that matters, it's also how far that force is exerted for, the distance by which that force is exerted. The work and F-net relationship and the work and distance relationship are both direct relationships. So you should be able to take a minute and derive that equation for work. Please pause this slide and figure out the equation yourself. So the higher the net force, the bigger the work, and also the further the distance, the larger the work. Move on to the next slide as soon as you figured out the equation for work. So hopefully on the last slide you figured out that work was equal to the net force times the change in distance of an object. And a reminder that another way to look at work is DeltaE, or the change in energy of an object. The units for work, we multiplied together a net force and a change in distance, so that's a Newton times a meter. If you remember a while ago, Newton is a kilogram meter per second squared, so that makes this a kilogram meter squared per second squared. And if you remember from the last slideshow, that's the same as a joule, which means that the units for work are the exact same as the units for energy. And that's a good thing because work is change in energy. So if they didn't have the same units, we couldn't add them or subtract them from each other. Let's do a couple quick practice problems with work. So if you have a car and it's moving at a constant velocity on the highway, is the work done on the car positive, negative, or zero? Pause it for a second to think about it. Okay, if you're back, hopefully you came up with the fact that that work is zero because the car is moving at a constant velocity, which means it's not gaining any kinetic motion energy or losing it. None of the energies that car has are changing significantly. You might say there's the chemical energy changing a little bit, but at any rate, by and large, that work is pretty much zero if an object is moving at a constant velocity. If a box is lifted up into the air, is the work done on the box positive, negative, or zero? So pause to think about this, please. Okay, so if you're back, you realize that that box from the beginning to the end gained some gravitational potential energy, so that should be positive work on the box. If a runner is slowing down, is the work done on the runner, that should say positive, negative, or zero. Take a second to think about it. And the work done on the runner should be negative because the runner has some kinetic motion energy at the beginning, and then it loses that energy as it slows down. So that energy is turning into something else, probably friction, heat with the ground or the wind. So it should be negative energy. And the last one is if an apple is falling from a tree, is the overall work done on the apple positive, negative, or zero? So pause for a second. The overall work on the apple should be zero because that apple starts with gravitational potential energy, but as it falls, it is gaining kinetic motion energy and losing that gravitational potential energy. So by and large, overall, we should have a relatively neutral or zero work done on the apple. The next new concept we're going to talk about is called power. And power is defined as how quickly work is being done. The variable we're going to use for power is a kind of a funky cursive capital P. And the units of power are the watt, which we'll come back to a little bit later on. You've seen that before, of course, on light bulbs, etc. But first, a question for you. Who is more powerful, a kid or a gorilla lifting weights? And that should be pretty intuitive just by your own definition of power, that a gorilla is more powerful. And the reason is because the gorilla can lift more weight. In other words, the gorilla can do more work than the kid. Who is more powerful, a Toyota or a Ferrari getting up to speed on the highway? Let's assume these cars have the same mass and they're getting up to the same speed. Well, they're doing the same amount of work this time because we are gaining the same amount of kinetic motion energy. However, the Ferrari did it a lot quicker, which means that the amount of time it takes to do something is going to be another relevant variable for power. So power depends on work and time. It's got a direct relationship with work. The more work we do, the more powerful we are. And it has an inverse relationship with time. The more time it takes, the less power, or the less time, the more power. So please take a minute and figure out what the equation for power should look like. Pause if you need to. So hopefully you guys came up with this equation. Power is equal to work over time. If we trying to figure out the units for power, work is joule, right? It's a kind of energy divided by time, which is a second. So power is going to be a joule per second. If we want to break this down into fundamental units, it's a kilogram meter squared per second cubed. Geez, these are getting really ugly. However, as I mentioned earlier, we're going to have a shortcut for that. We're going to call it the watt. So if someone says, "What's the unit for power?" you can say exactly. Ha ha ha. One of the tricky things about the watt, of course, is that the abbreviation for watt is a W, but the variable for work is a W. I don't have much of a solution. You just have to keep them straight on your paper or in your brain. Couple quick power practice problems. If it takes a cat 3 times longer than it takes a dog to drag a toy upstairs, the same toy, which animal does more work and which animal is more powerful? So pause to think about that for a minute. So both animals do the same amount of work because they're taking the same object and increasing its gravitational potential energy by the same amount. However, the dog is much more powerful than the cat because the cat has more time, which means because of the inverse relationship between time and power, the dog is going to be more powerful. Next question. Joe can lift 40 pounds and his brother can only lift 20 pounds. Is there any way his brother could be more powerful than Joe? If so, how? If not, why not? Pause to think about this. So there's actually several ways his brother could be more powerful. Maybe the brother is lifting that weight to a higher height, okay? Because the more distance that you do work over, the more distance that you exert your force over, the more work it is. So if we can lift more than twice as high, then we might be doing more work. Or we could be doing these lifts in much less time. So half as much time or smaller, and his brother would have more power than Joe. So there's lots of different ways that we could get to that result. Just the amount of weight that we lift is not the only thing that matters here. So to summarize work and power, I know this has been a little bit of a dense slide, or slideshow, but I really encourage you to go back and watch it once or twice more, especially thinking through those practice problems if you felt like they stumped you. Work is how much an object's energy changes. This can be any kind of energy. So it could be gaining energy with positive work, or negative energy, losing energy, negative work. And power is the rate or how quickly an object's energy is changing. Thanks for listening.